Welcome. In this video, we looked at drawdown in the previous video. In this video, will be more quantification. Like we will try to quantify drawdown at steady state, and then next video we'll look at try to quantify this and put it in an equation for transient flow. So by the end of this video, you should be able to describe the basics of well hydraulic, including aquifer response to pumping and radial flow. So you'll be able to quantify this with some equation. And you will be able to use this equation to estimate drawdown and transmissivity for when you start at steady state flow to a pumping well. Yeah, using this equation. Okay, so we will have an equation. We can use it to estimate the transmissivity of the aquifer, or we can use it to estimate drawdown. So we've seen this already before in the previous videos. This is just like a review. You have a well here. This is your static water table, like your pre-pumping level. And once you start pumping, you will have like drawdown, like your your groundwater level will drop if this is an unconfined aquifer, so your hydraulic head will drop. But the most important thing, remember, the most important thing from the previous video is that this would be like a radial flow. Like if you have like a bird view, like a top view, that would be, oops, uh, that would be radial flow. So the head will drop would be like, so if like you're pumping from here, and that would be like a radial flow. So the head here would be similar to the head here, would be similar to the head here, would be similar to the head here, would be similar to the head here. Yeah. So like if you see here, this is like radial flow. Yeah. This is radial flow. Like you can, you have like, this is like, that's how like your drawdown will look. Okay. So under this assumption and other, remember, like to come up with this analytical solutions, we generally come up with some simplifying assumption. Numerical solution, you don't need this simplifying assumption, but for analytical solution, like a closed form or infinite series, we have this simplifying assumption. So like the governing equation is that compressibility is strictly vertical. So the compressibility is only in the vertical direction. So here we are doing this for like a confined aquifer, yeah. So because confined aquifers, that's where you have compressibility, and I will show you this equation for confined aquifer. But it again for an unconfined aquifer, you also have some compressibility. Remember, because there is a water and air column, so water is still compressed, but not as in the unconfined aquifer. Water release instantaneous as head drop. Vertically integrated flow equation, so vertical gradient are negligible. So that is important, like you don't have like a vertical gradient, these are negligible. Aquifer characteristics. So the aquifer, so that's the simplifying assumption, the most important one. Homogeneous and isotropic aquifer. So you can get like this radial flow. Constant thickness, the aquifer thickness is not changing in space. Hydraulic head is uniform prior to pumping. We've seen this. I showed you in the, so you see here it's constant prior to pumping. Aquifer is horizontal and infinitively large in the horizontal direction. So you have like horizontal aquifer and infinitively large in this direction, in this horizontal direction. Yeah. Aquifer and infinitely like well pumping characteristic, single fully penetrating well pumping at a fixed rate. So here it's like a single, it's fully penetrating, so it penetrates through all the aquifer, and the Q here is like how much water you pump out is constant, and it's fully penetrating. See, it penetrates throughout the aquifer. Okay. So fully, the diameter of the well is infinitively small. Like, so this well diameter compared to like your aquifer length is this is like very small. Like you see, this is very small compared. So that would be like few centimeters. That would be several kilometers or several meters or hundreds of meters. Yeah. Okay. So under this assumption, this is our flow equation in 2D. Yeah. So this is our flow. We've seen this before. So this is our flow equation in 2D for confining aquifers, basically showing you like how head is changing in time uh, relates to how head is changing in space, and this with some proportionality constant related to storage and transmissivity. Yeah. But to find like a closed form solution for this equation and to take advantage of the fact of like that we have like radial flow, we can change this one from Cartesian coordinate like x and y, like how head is it changing in x and y, to how head is it changing with respect to r and theta. Yeah, so here is theta. So this is a Cartesian coordinate, and we can change this to like a radial or like radial or polar coordinate. So basically, what does this mean? So here, like, what is the head here, for example? Yeah, so the head here, like this is in this x direction, and then in this y direction, and then you can calculate the head here. Uh, another way, so that's my point, yeah, where I want to find the head. Yeah, that's what you want to find. Another way to express this is instead of saying, okay, like I move in this x direction and then I move in this y direction, is that like you could have this radial component where you have r. So I have an r here, and then I have a theta. I have a theta here. So that could be like my r could be like until here, and then I move to theta here. Yeah. Or my r could be up till here, and then I move to theta here. But the advantage of doing this is that we take advantage. Remember, I told you that h, like let's say I'm interested in h will change with r. So here, this is the maximum drawdown. See, like here, that's where you get the maximum drawdown. When, like, let's say you're pumping from here. Let's say I'm pumping from here. This is my pumping well. So here I will have my maximum drawdown. As I go far away from where I am pumping, the drawdown would be zero. Do you remember this? So let me show it to you again here. So like you see here, this is my maximum drawdown. This is my maximum drawdown, like maximum change in H. While if I go away, like see here, H is not changing. Let's say here, H is not changing. So as as the distance from the pumping well increase, my head will not change, like drawdown will not change. I will have the maximum drawdown here, and then that's everything in between. Okay, so that's what we are see like this. So, oops. That's what we have here. That like if I'm pumping from here, I will have like maximum drawdown here, and as far as I go, so H is only changing along R, like how far I am from my pumping well, but it's not changing along theta, because remember this is radial flow, so that's like my head. So my head here is like radial flow here would be equal to here, 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 would be equal to here. Similarly here, like at any point from where I am pumping, see it's radial flow. So RH is not changing. That's the most important thing. Like the delta H over delta theta is equal to 0. H is only a function of R and T, like how far I am from pumping and the time, just as we see here. Yeah. So H, see, at different interval of time, my H is changing, and at different location away from where I'm pumping, my H is changing. So that is the most important thing here. H is only a function of R. Oops. H is only a function of R and T, and independent of theta, like delta H over delta theta is C. And then I can, of course, express like, you can always express like R as X, that's R. So that's R. So what's R, like Pythagoras? That's like X, and this is Y. So R is X square root of X square plus Y square. Theta, you can express it like as tan like x over y. This is like theta here, uh, opposite over the adjacent, like, remember this? Opposite over adjacent, yeah. Remember something like this. But anyway, so let's if you remember something like this, yeah. Okay, so that's basically, so if I like use like the chain rule, if I use the chain rule, then I can express like my delta H, how delta H is changing with delta X. I can do the same for Y. I can relate it to how like a delta H is changing with delta R, and delta R is changing with delta X, yeah, and how delta H is changing with partial H is changing with partial theta, and how partial theta is changing with partial X. And if I did this, and I'm not gonna show you like this derivation here, like the mathematical derivation is not important, but if I uh, did this differentiation, then I could express like my equation, my flow equation in 2D in X and Y. I can express it just in terms of R. Theta is not important, yeah, because remember, like delta H over delta theta partial, sorry, not delta, partial H over partial theta is equal to 0. So I end up with this form of equation. So this is basically like we have two form of now of our groundwater flow equation. We have one form in the Cartesian coordinate in 2D, and then we have one form in the radial coordinate. And now that's very good, because now here this is like two, like actually 3D, because I have like H is changing in X, H is changing in Y, and X is changing in time. So it's like a 3D equation. Here I only have a 2D equation. H is changing in time, and H is changing in R. Yeah, how far I am from pumping. Yeah, with time. That's it. Yeah. So again, like the mathematical derivation, like how we got from here to here is not important, but you can try it. Like, so basically, like you can follow this step, like find the first derivative, find the second derivative, and then back substitute here. And if you did this, then you will get something that looks like this. Yeah. So I'm not going to show you this, but if you try to do it on your own. Here is the solution. Like if you want to see like how we got, but again, like this is not important for, I mean, this is not a math class, how we got from here, from a Cartesian coordinate to here to polar coordinate. So this is steps. Yeah, you can follow this derivation steps if you're interested. So try to do it on your own, and then maybe check with this solution here. But anyway, let's get back to our what we want to do. So what we want to do, we want to find like an equation where if I know pumping, if I know Q, I could like, if I know pumping, for example, and I know uh, change like drawdown, like a change in X, then I can estimate K. Or if I know pumping and I know K and I can estimate H. Like I have three unknown, like I have Q, how much I'm pumping, have H like change in head, and K like the uh, hydraulic conductivity of my aquifer. So if I know any of these two, I can get like I can get the third one, and you can use this for different scenario depending on the objective of your analysis. But let's look here. Yeah. So here we have like if we looked here, Q, like, so that's like a flow, and that's like small q time A. So you remember this already. And small q, that's Darcy law. Do you remember what's like small q? Small q is like K time delta H over now. Now here, I'm not expressing it as delta R, as delta X. Yeah, I'm expressing it as delta R, how far I am like from my pumping. Yeah. And now, like, what is the area? Like, see, now the area is that would be the area of this cylinder here. So that would be like pi r. Yeah. So that's like 2 pi r. and time B. Yeah, so if I like 2 pi r time B, like B is like your aquifer thickness, that will give you the area. Uh, and then we also know that transmissivity, do you remember like transmissivity is K time B, like so times the aquifer thickness. So this is like transmissivity. So I can change this for transmissivity. And what is R? This is the radial distance from my pumping well. Yeah. So and delta H over delta R, this is hydraulic gradient expressed. Yeah, this should be expressed as the changes in head with radial distance R from well. Yeah, from the well. Let me discard this. Expressed. Yeah. Expressed as a change in head and radial distance. So, okay, so that's Darcy law basically in radial coordinates. So we've seen like the groundwater flow equation like in radial coordinates. That's like here we have our Darcy law in radial coordinate. Okay, so this is R and this is B, and this is like a systematic. Okay, so now giving what we know already about Darcy law in radial coordinate, like we have like the seam equation, and the seam equation, this is for well pumped long enough that water level reaches equilibrium with no further drawdown with time. So this is for the case of this case. This is for the case of here we go. This is for this case where this guy is equal to 0. Yeah. Oops. This is for the case where delta H with delta time is equal to 0. Yeah. And basically you only have delta H is changing with R, and that's basically would be Darcy law. So that would be like your Darcy law. Yeah. So here Q, like we've seen this before, yeah. And then now we want to we have like this differential equation. What do we want to do here? We want to solve for H. So how to solve for H? Like, do you remember from your calculus course? You basically integrate, yeah. So this is like so you do like separation of variable here, and then you integrate here with respect to H, and you integrate here with respect to R. So this here from H1 to H2. So here I'm pumping, this is where I'm pumping from. And then H1 to H2, that basically would be like any like two head in your system. So if I like know the head here, for example, and like the head here, or any two like head, like where you want like your system, like your H1 and H2, and then R is the distance. So like R, so at H1, like you have R1, yeah, and at H2 you will have R2. Okay, so basically you have like H1 and R1 and H2 and R2. Okay, so if you did this integration, like if you did this guy here, that will give you like H2 minus H1, 1 over R, that's len, and then you substitute this, so this R2 over R1, and then you could arrange your term, like you can express this in different way, like you can express it in H, or you can express it like you arrange term and express it in in T, and that depends on the objective of your analysis. So like if the objective of your analysis, let's say like I have my house here, like let's say I live here, yeah, I have my house is here, and then I have like a domestic well, yeah, and then I have like some guy who's pumping here, yeah, big somebody who's pumping here, and then I want to see what would be the H2, like so what would be the H2, so I can calculate like drawdown, yeah, like what would be the H2, I can calculate drawdown to see if this well will go dry or not. So in that case, how to solve this problem? What do I need to know? I need to know, like, I need to have like a monitoring well. It could be also your monitoring well could be also where you are pumping from. That could also be the case, but I need like a monitoring well where I find like H1 here, and I need to know like how much this guy is pumping water. So if I know how much this guy is pumping water, and if I know like the head here or the head here or the head here or the head here, like at any other point, my system, and then I know like the R1 and R2. So if I'm measuring like head here, for example, yeah, what would be R1? R1 would be like just the diameter of the well, yeah, just from the center of the well to here, yeah, to the casing, yeah, from the center of the well to the casing. So that would be R1, yeah. If I'm measuring if my H1 is here, yeah. If my H1 is here, then that would be like your R1, and so on and so forth, yeah. So I may like this I can measure, this I can measure, I know how much I am from this pumping well, and then I could find my H2. Then I will know, okay, H2 here would be this. This is my well screen, for example, is here. Then maybe this well will go dry. But if my well, for example, is going down until here, for example, then it will not go dry. Something like this. So that's how you could use this analysis for to make these estimate. Yeah. Another way is that, like, let's say I know how much I'm pumping Q. Yeah. I know like H1, like I have two monitoring well. I have a monitoring well here and I have another monitoring well here. So I know H1 and H2. Then, and I know the distance from H1, how far it is from my pumping well, and H2, like how far it is from my pumping well, like where I took this measurement. Then I could estimate the transmissivity of this aquifer. So that could give me information about the aquifer itself. Yeah. Uh, so that could give me information about the aquifer itself, and then that could be used for planning purpose. And we will learn more about this later. So steady state radial flow to well in a confined aquifer. So this is called like the theme equation, THIEM, theme. Yeah. It can be used for drawdown. Yeah. So here, this is, I showed you already. We like to estimate drawdown, like I told you this already. Like, so what is drawdown? Drawdown, that is your initial head minus your H1. So that is like a drawdown. So let's say here, let's say like what is, so that was my initial head prior to pumping, yeah. So this is like my static level, like H0, yeah. And then after pumping, yeah, my head dropped from here to here, yeah. So now this is my H, yeah. So let's call this H1 or HW or whatever. This is from where I'm pumping, yeah. So what is drawdown? Like draw down like W, for example. That would be like H node minus HW, yeah. How about here? Like see this guy here, like draw down here. Again, so this is my initial water level, yeah. So this is like, so S1, yeah. So this is H0, like this my initial water level. From here to like my datum here, yeah. And then after pumping, this is the head, so this is will H1, and that will give you here this part like as a drawdown, yeah. So that would be my H naught, so that's like H naught. This is minus H1 minus like, so this guy minus this guy will give me this guy here, yeah. So simple, yeah. And same for H2. Where would be your maximum drawdown? Like where would be like your maximum S? Is it would be at SW, S1, or S2? Yeah. So obviously your maximum drawdown here is SW. Like see, this is SW, this is S1, and see, this is S2. And as far like see, like if the further I go away from this pumping well, like see, the further I go away from this pumping well, then like at S like infinity, then the drawdown will be zero, yeah, because there will be no drawdown. Like as far as the further I go from this pumping well, then S will be in infinity. Yeah. Uh, and I told you this is possible to use H1 instead of like HW, like where you are pumping from, instead of H1 and H2. In that case, so like here in that, like if I'm using H1, this is R1, yeah. If I'm using H2, this is R2. If I'm using HW, what would be my RW? So my RW would be from the center of the pumping till here. That would be my RW. Yeah. That's R1 and that's R2. Okay. Uh, Let me see how we are doing in timing. Uh, okay, so timing is good. Uh, Similarly, I already told you this. Similarly, I could use this to, oops. Similarly, I could use this to estimate transmissivity, like how much uh, water can this aquifer give us. It can and this is an important, like as we will see later, this is a very important modeling parameter, like hydraulic conductivity or transmissivity, because you need to define your hydraulic conductivity field, because that's where the flow will occur. That's how you will know about your flow, and that's the most important parameter for developing a groundwater flow model, is to know this how the subsurface look like, and to put and different hydraulic conductivity zones or something like that. Yeah. And we will like next set of videos, they will be about doing this, like doing a pumping test. So the objective of the pumping test would be mainly to estimate transmissivity and the storage coefficients. That's why we do a pumping test, and that's how we, one way of learning about our subsurface. So we can learn about our subsurface through a pumping test, as we will learn next, or also we can use geophysics, hydrogeophysics method, like doing imaging, like subsurface imaging. And typically we use both, like, or not typically, but we can use both, yeah. And in your project, for example, you will use both. So in your project, you will estimate transmissivity or hydraulic conductivity. You will estimate like K, hydraulic conductivity, from pumping test data that I will give you. And you will estimate also hydraulic conductivity from geophysical images that I will give you. You'll do both. And that's how you will define your flow field, and that's how you will set up and calibrate your model. Yeah. But you'll learn this later. So this is an example. Oh, I shouldn't discard. This is an example. I shouldn't show you the solution. So this is an example. It's very simple, yeah. Like just try to solve it, and it's basically telling you like find the transmissivity. So, oops. So you have like an equation for this. I mean, it's the same equation, yeah. So here, like what you need to do is just make sure that your units are consistent. So Q is given, yeah. So Q is given. This Q is given here. 2 pi, like transmissivities, this is unknown. And then H1 and H2. So here, this is like H1 at R1, like R1 is equal to 25 meter. H1 is given here as 85.3, yeah. And that R2, like R2 is like 75 meter. H here is giving at 89.6, yeah. So that's like the H here. Uh, and like the further you go, you get like higher head, yeah. Okay. You get higher head. Yeah, so basically H1 is giving, H2 is giving, R1 is giving, R2 is giving, and then you can easily solve for T. So try to do it. That's a good practice for your homework. Yeah. And then, so if you did this and your unit is consistent, then like that's the transmissivity value you get. 16.3 meter cube per meter square per hour. Yeah. Okay, so that's a good transmissivity value. Yeah. Okay, this is the seam equation. I'm telling you find the drawdown here. So I want like to estimate like drawdown here. Yeah. So I'm telling you what's the drawdown here, like SW. And remember SW or SW, that is which one? That is S0, like my original head value here. So that's like, or not S0, like H0. So that's like my H0 minus my HW. Yeah, that's like this value here, this guy here. So if I know this guy and I know this guy, then I can estimate like this guy here. Yeah. But do we know this guy here? Yeah. Or how can we find like this guy here? So like to find this guy, we can easily find this guy because like we can either like use this guy or this guy, and transmissivity is given. Remember, like transmissivity, we found already, like we can use like that's the solution strategy for this. Basically, like you use two these pieces of information, you substitute them here, and you find t value. That's what we did before, and t value was I think 16.3 meter square per hour. Yeah, so we can find like 16.3 meter square per hour from these two information. Yeah, because q is given, and from these two information we can find like this guy. Now I want to find like HW, yeah. So I can say like this is like HW, yeah? H2 is HW. Then I can use any of my giving information. Like I can use this one, yeah, here. So I can say like H1 is giving like 25 meter, Q is giving, this is like 400 here, T is giving, uh, R1 is given, that's like 25 meter. But what's R2? Like R2 in that case would be RW. RW, that would be like, yeah, here. See, you see here, 2RW. So that would be the distance from here to here. But are we giving this information? Like, are we giving like what is diameter of this borehole, or like are we giving this information? We are not giving this information, so this problem does not give you this information. So basically we can just assume, like we can assume that the diameter of this guy here, like the d diameter, the w is, oops, is like 1 meter. Yeah, and then so that in that case rw would be like the radius would be 0.5 meter. Yeah, so in that case r2 or rw could be 0.5 meter. Okay, so yeah, so now I can solve for hw. Yeah, so if you did this, like you can get like hw, whatever number you have here, you are giving h node, like so h node was given, are we giving, yeah, the drawdown is giving, so here S node, like, or we are giving here like H node, like, so this is this should be the drawdown S giving that this should be H node, yeah, not S node, like giving like that this guy is equal to 90. Yeah, so so you solve this, so basically, so SW, that would be 90 minus whatever head I got from here, and that will give me the SW thing. So let me carve out of error. So if node is going to be equal to 0. Okay, so try to solve it and try to solve it again. I just and then use, for example, like this one instead of this one. But here, I mean, that's the same. So here I'm solving it using this one. Here I'm solving it using this one, and for both I'm getting the same information. Then SW is H node, like which is 90, like 90 meter, minus HW, whichever one you calculated from here, and then you get 20. Okay. Uh, this is same slide. I'm just repeating it. Yeah, so this is the same slide, and I'm just like repeating it somehow. Okay, now let's. This is the final slide for this lesson. What we did before was we were looking at the drawdown, yes, from unconfined aquifer, and for confined aquifer, and for confined aquifer, the B is the saturated thickness does not change, but here's the saturated thickness for a confined aquifer, it changes, yeah. So B is no longer constant, and the saturated thickness it changes. So in that case, my 2 pi r times B here, that would be H, that would be changing. So, but again, it's the same thing. Like all I did here is that like this is my B, but my B now is changing, so it's H now, yeah. So now like for this, then I will integrate H over dH square, and then for this you get like H square, yeah. And you get like here H square. So that's like when you do this integration, and then like the 2, like H square over 1 over 2, and then this 2 will go with this 2, and then you get only pi k q. That's the only difference. Remember, the other one was h, like h2 equal h1 plus q over 2 pi k, or b time k, which is like transmissivity. Here you get like this equation. So, and then you can also arrange the term and find it in terms of q. But it's the same thing, yeah. And you know how to do this integration. Okay. So I think that's all for this lesson, and I will just like see you in the next lesson. We will be learning about the transient drawdown.